v, right? This one here is v, this one here is u, right? Then the resultant vector is equivalent from the vector of the equivalent to the vector from the tip of what's this one? For us, this is v, and then this one is u. From the tip of v to the tip of u. So it should be the other direction. That right there is this. Now what you were saying, right, is would be, or you could say v minus u, right? So if you want to draw this one that goes this way, then that would be the vector v take away u. We need that before we can do anything. Yes?
What about mechanically? It would just be the subtraction, right?
Yeah, it's just subtraction. This is more of, can we visually understand what the difference of two vectors is?
Gotcha.
So if we're going to take u and subtract v, right? U and subtract v, it's going to be the vector that goes from here to here. If we do v take away u, it's going to be the vector that goes from here to here, right? All right, here we go. Let's start getting and trying to define a line in a new manner. Whoa. We're going to stick in two-dimensional space just for simplicity to start. All right, let's look at this blue line. A line is basically just a collection of points, right? Just a bunch of points. First, we want to notice that for every point on this line, there is a vector that goes from the origin to every point on the line, right? Right? Yep. Every point on that line has a vector that goes with it. Now, there are infinitely many vectors, right? Mm-hmm. But all those vectors point to all the points on those lines, right? Or all the points on those lines, on that line. So what we're going to do is we're going to define a line for us now to be those vectors. Instead of those points, it's going to be the vectors that point to all the points. That's going to be our definition of a line. So this is it. Vector equation of a line in two-dimensional space. The vector equation of a line is an equation which generates all the vectors from the origin to every point on that line. That is our new definition of a vector equation of a line. Yes?
And this is kind of like outside the course, but isn't that the same as like span?
Same as what?
Span?
Span of?
Linear algebra.
Well, we're only talking about a line, right? It's one-dimensional. So, well, kind of. Yeah, I mean, I guess you could say the span of a line, like, you know, in one-dimensional, you do have span. All right. Everyone understand what we're trying to achieve here? We're going to try and, instead of like giving all the points on a line, we're going to try and come up with all the vectors that point to all the points. Yes? So how do we do that? We're going to start constructing it. Ready? Let's say that we're given a point, right? Remember, we need at least one point on a line to define it. Well, actually, we need two, right? Let's say we're given one. We're going to call it x naught, y naught. Notice this is not a vector, that's a point. There it is, right there. That's the point x naught, y naught. First thing I'm going to do is I'm going to define a vector that goes to that point, r naught. How should I define that vector, r naught? What should the x and y components of that vector be? X naught, y naught. Well, not minus, hold on. We're just going from here to here, right? This is the point, x naught, y naught. So if I define my vector to be x naught, y naught, but as a vector, then won't that point to the point x naught, y naught? Right? So r naught points to x naught, y naught. Yes? I have one vector. I need all infinitely many of them, yes? Next step. I'm going to take another point on that line. That's our x naught, y naught. Here's another point, x1, y1. That's the second point, right? I need 2 points to define a line, so that's got to be given to me, at least 2 points. So that allows me to define a second vector, doesn't it? Okay, so I'm going to call that R1. So out of the infinitely many vectors, right, out of the infinitely many vectors that point to all the points on that line, I have 2 of them, don't I? 2 of them so far. I need all of them. The next thing I'm going to do is I'm going to go ahead and do this computation over here. R1 take away R0. Now I show the work here, but let's skip to the next slide because it's better. Do you all agree that the red vector V is this vector R1 minus R0? This is what I just started with. Remember when I was saying that we did the preliminary stuff, right? That's exactly what this is saying, right? If I take R1, that vector, and subtract that vector, I get the vector that goes from the tip of this one to the tip of that one, right? So that's what V is here. You all good? Now I want you to notice something. What if I took R0 and I added V? That would be the same as what vector? R1, right? R0 plus V gives me that vector, right? R0 by itself gives me that point right there. R0 plus V takes me to that point. Yeah? But what if I do, forget R1, what if I do R0 plus 2 V's? So I scale the V by 2. Won't I be out here at a point right here? Yes? And that would be a third point on the line, wouldn't it? But I could have scaled it by another number, right? I could have taken the R0, taken that V and multiplied it by -1. It would have put me over here. That would have given me another point on the line. Right? Or I could have done any scalar multiple of V plus that R0, and I will land anywhere on that line, won't I? So what is it that I really need to do this? Like, in order to figure out all the vectors, I really only need one vector, right, going to one point, and then this very important red vector, right? That red vector allows me to scale and go anywhere I want on that line, right? So the R0 takes me to the line, and then the V takes me in both directions on that line. You see that? So so how do we generate all the vectors, right? We take all the multiples of V and add it to the R0. So here's the general formula right here. This is the big takeaway. I'm going to write it over here on the board. R of t equals R0 plus TV. So this is, the analogy here is this, if you want to look back to college algebra. Remember that from college algebra, right? This is the equation of a line written as a function, right? Pardon? Okay. This is a function, right? In college algebra, this is mx plus b. This is the slope, right? This is your variable. This is your y-intercept. It's similar to that, but we're using vectors. We have this r of t is like the f of x. T is the input. Think of t as like time. Plus R0 is kind of our starting point, and then plus t, which is like the x here, and then this v is like the m. The v is like your direction, like your slope, but v is now a vector.
So we'd have to figure out v to effectively plot it.
You've got to get v. And that v is very important. Like it's the essential thing is v. And that's why it has a very important name. It's called the direction vector. Now, I believe in your notes I did not put vector. You can say it's the direction of the line, but I'm going to go more explicitly and say that v is the direction vector. So I think the best way to see all this play out is to just do an example. Let's just do one first, and I'll get back to all of that. We can at least do the first part of this. Maybe first, we'll do the first two. All right, so I give you a point, right? 2 points in space. It's two-dimensional space, right? And I tell you that they lie on a line, and I'd like for us to find the vector equation of this line. So I'm going to take the 2 points here, 7 and 14. First thing I need to do, if you're thinking about this visually, I really don't care where these points are, to tell you the truth. Okay, but let's say that this one's 3, 6. Let's say that this one is 7, 14. First thing I need to do is create my R0. I need to get from the origin to any point on that line. So I can go from the origin to here, or I can go from the origin to there. Completely up to me. I'm going to choose to go from here to here and define that to be my R0. So as a vector, R0 for me would be 3, 6. Okay, that's my R0. The next thing I need to define the vector equation of the line is I need V. I need the direction vector. And to get the direction vector, all I need to do is find the vector that goes from that point to this point, from here to here. You could also go from here to here, but to follow what I showed you visually, I'm going to go from here to here. So I'm going to go take the vector that goes from here to here, which would be 7 take away 3, and then 14 take away 6. That's the vector for 8. This is the very important direction vector. And so finally, the vector equation of the line is just those things put together. So R of t equals this vector 3, 6 plus, so that's R0 right there, right? That's R0 plus t. T is a scalar, right? That's the thing that's going to allow us to stretch out that v or point it in the opposite direction. So I'm going to put t here in front of the vector 4, 8. Any questions on that? We're good? Now I could leave it like this. This is fine to leave it like this, but I want to show you, you could also do this. You could push the t through, you could scale. So make this 4t, 8t, right? That's scalar multiplication. The t goes through.
You want the t inside?
No, I'm saying you can do that, right? This would be legitimate for me to do that. Mm-hmm. And then there's one more thing I could do if I wanted to. I could actually add these vectors together, couldn't I? Mm-hmm. So to add them, you add their components. So you'd have a vector 3 plus 4t. I can't put those together, right? Because one of them has a t, the other doesn't. And then 6 plus 8t. This is the vector equation of this line. But those other forms are equivalent forms for that vector equation. Which one you use is completely up to you. I kind of switch back and forth. I really like this one, though, because this one right here allows me to do part B. Find another point on the line. So I've given us 2, right? Let's find a third. Plug in what? Okay, well, all right, take this equation right here, this vector equation. Let's try it. Plug in 0 for t. What do you get? You get 3, 6. That's the first point, right? Plug in 1 for t. What do you get? 7, 14. That's the second point, right? Plug in some other value for t. 2, negative 1, 5, 7.23. Doesn't matter, right? Every single value you get out when you plug different t's in will give you points along that line, right? So let me just do one specific example. Let's do r of 2. This will generate the vector, let's see, 2 goes in here, right? 8 plus 3 is 11. And then 2 goes in here. 16 plus 6 is 22, right? Everyone understand what I'm doing there? Okay, that is a vector, right? That is a vector. Part B is saying find another point on the line. So what would the point be? 1122, but written with parentheses instead of the angled brackets. Because that's a vector. It points to the point, right? So to answer part B here, find another point on the line. The point 1122 would be another point on that line. And that's only one of infinitely many answers you could have got. Yes?
So here's a question, because I jokingly said it. Could you plug in something like pi?
Yes.
Okay.
Yep, I almost said pi, actually.
Okay.
Any number you want. Any number you want in for t, and it will be somewhere on that line. Yes?
So it's just kind of like a parametric equation?
So yeah, that's exactly what I'm going to say now. These equations right here, this equation right here, and this, sorry, I shouldn't say equation. This expression right here always gives you the x coordinate or x component of the vector, right? This always gives you the x component, and this always gives you the y component, doesn't it? And so we have a special name for those. It is called the parametric equations of this line. So this is in the notes. I'll scroll up and then I'll come back down. I'm going to erase this here. What do I want to keep here? Say again?
This allows you to find.
This allows you to find 3D what? Points or lines in three-dimensional space. Yeah, if you have a line in three-dimensional space, we can come up with a generic equation for that line, then find all the points on that line. All right, so look at what this says. Now that we're going to roll it back, and let's see if this all makes sense now. Let's say that you have the R naught, right? Remember how we generated the R naught? Okay, and then we calculate the V, which is going to be the vector going from one point to the other. Then you have this formula, R of t equals that R naught plus t times the V. Then you put them together, right? You distribute the t through and then put them together. These two things, which is these two right here, those things are known. These give you the components of the vector, right? This one and this one, the x and y components respectively, are called the parametric equations of the line. Right, that's what they're called. Further, the A and the B, so y'all see that right there? Our direction vector V, it has two components, A and B. What were those numbers for us here? Can you tell from looking at this what the A and the B were? A was 4 and B was 8, right? A, B, right, are known as the direction numbers. So the direction numbers of this line are the numbers 4 and 8. Those are our direction numbers. Now the last thing, and this is kind of strange, is that if we take the parametric equations and we solve them for t, then we can get something called the symmetric equations. I want to show this to you, all right? Because symmetric equations are kind of confusing until you see it worked out. So let me get myself a little space here. I think we can continue on this. We answered that one, didn't we? Part B, we answered. Another point on line, 1122, yes? Okay, now let's find the parametric equations of this line. We're answering part C. We already had this, don't we? X is equal to 3 plus 4t. And then comma, the y is equal to 6 plus 8t. Notice there's no vector notation there. It's just what's the x going to be? What's the y going to be? Yes, sir.
Could you just go right to that if you know your parametric equation instead of having to do the starting with your vector line formula?
You said, can you go right to that if you have the what?
If you know your parametric equation setup.
If someone gives you your parametric, then you can go to the
If
vector.
someone gives me my vector, could I just go right to this?
Your vector,
Yeah, if someone gives me my starting vector,
okay?
like to set up my, my vector line equation.
You need 2 points.
Yeah.
Then you create a vector,
Yeah,
and then a vector going from one to the other.
yeah. Basically, I'm asking if I'm given this setup like we were given here, could I just go right to this part? Here.
You'd have to calculate 4/8,
Right. Okay.
right?
So you still have-
4/8
you
is
still have
not
to do
given to
some-
you.
You still have to do some calculation.
That's right.
Gotcha.
3/6 is there, right? But the 4/8's not.
Okay.
Those you would have to calculate. All right, so these are the parametrics?
Yep.
Yes? Now we're going to try and get what are called the symmetric equations. And the way to get symmetric equations is to take both of these equations and solve them for t. So let me do it, and then just let's see how things go. If I want to isolate t right here, I would first subtract 3 on both sides. All right, I'm going to work with these separately. And then now I would divide both sides by 4, yes? Questions on that? Do the same thing for the other one, other equation. So take your 6, subtract 6 on both sides, and then divide through by 8. Yes?
Well, obviously in this case it's equal. Well, there should be equal because they're both the same thing, but what happens if they're not equal in this case?
What do you mean they're both?
The t's, because since they're both the same variable, they both have the same value.
Exactly.
So it'll weight, like he was saying, their output spans.
Well, the whole point of doing this step is that if both of these are linear equations, right? These are both linear equations. You should be able to solve for the variables. So I should be able to solve for t, right? And this will always be t, won't it? It's not going to be like t squared or anything like that. These will always have t on both of these. And since both of those are equal to t, you can set them equal to one another, can't you? So I can set this equal, and I can say x minus 3 over 4 must equal y minus 6 over 8, right? I can say that. This is called the symmetric equations, or symmetric equation. It's the equation that also associates these two things, x and y, together. Was there a question over there? Yes?
If it was t squared, you could just take the square root.
Sure, but because remember that this is a line, right? And so the way we set up this formula, we will never have t squared here because this will always be t, right? But if so, we could do square root. Hey, guess what? That right there, if you were to rearrange things, you'd be back in college algebra. Do you see that's an equation just has x and y in it? So if you rearrange things and solve for y, you would get the traditional college algebra form of the line. That's what you would get.
Does this line have a slope of 1, just looking at that? 'Cause
Well,
that looks
you would
like
have
y-
to, no, you would have to solve for y to figure it out. Yeah, move things around. So let me recap. Someone gave us 2 points, right? 2 points in two-dimensional space. And from that, we were able to come up with 3 different versions of the line. The first version we had was this new thing called the vector equation, which looks like this. Plus 4t6 plus 8t, right? That's the vector equation of the line. This is new to us. The second thing we came up with was something called the parametric equations, which is just listing out the x and y components, right? And then the third representation of this line was the symmetric equation, which was this. They all have their pros and cons. Let me explain pros and cons here. This would be very easy to generate points, right? I could just plug in different values of t, and I'd get points all over this line, wouldn't I? Would it be as easy to do here? No, because you don't have t, right? So you'd have to plug in an x and then go figure out what the y would be. Or plug in a y and go figure out what the x would be. See, it's a little harder. The other thing is this, though, when you look at this, it's pretty simple to see the direction numbers, right? 4, 8. Those are your direction numbers. So there's pros and cons. We should be comfortable with all three forms, right? Yes?
So if they give you the equation of a line, instead of going through the RO, RTB, we can just go ahead and try to manipulate it and make it look like that.
Yeah, so check this out. This is a great question. Look, let's go back to college algebra for a second. And let me give you this right here. Y equals negative 3x plus 4. I wonder how hard it would be to get it into these, all right? So here's what I could do. How about this? See if you buy this. I'm just going to do this to make the sign. I guess can't get rid of that negative. Do it this way. Okay, you okay with that? Mm-hmm. Now I'm going to divide both sides by negative 3. Mm-hmm. What would this be on this side? X, right? So watch. This is the cool part. I'm going to say X. Anyone see it?
X minus 0 over 1.
Minus 0 over 1. You all see that? Look, does that look like this right here? So what is a point on this line? Like, think back to this one. What was a point on this line? 3, 6, wasn't it? So do you see how these numbers give us like the 3, 6? And then this gives us the direction, right? So what would be a number on this line? Or what would be a point on that line? 4, yeah, 0, 4, very good, because the x and y are switched. So 0 for x. So 0, 4 should be on this. Is it? Plug it in. 0, do you get 4? Right? So that's our symmetric, right? Does everyone see how we did that? It's a little weird, right? But we could do that. And then from here, couldn't you go back to this? Or one of those? We could go here. We go to this one. I would go R of t equals, all right, I need a point, right? This right here, this was a point on the line, which for us we said was 0, 4, right? 0, 4. So I could put 0, comma 4, then plus t in front of the direction number, plus t in front of a direction number. What are our direction numbers here? Go in the order of x and y, right? So 1, so I go 1 there, and then here, negative 3. Y'all see that? I'm not going to ask you to do this, but I'm just showing you, like, you could take what you learned college algebra, and now you could go recover the symmetric and go all the way back to the vector form if you wanted to.
I like how there's a relationship there.
There is.
That's it.
That way we can make any type of function related to time,
Any linear,
any 3D coordinate.
any line, you could go and make it a function of a single variable by finding its parametric representation.
An original function that's in 2D and you want to translate it over to a 3D coordinate system. That's how you kind of think about it.
We're still in two-dimensional space right now. We're still in 2D. I'm about to start 3D. Okay, so up to this point, these points were in two-dimensional space, right? Flat sheet of paper, but we can extend the same ideas out to three-dimensional space. So see if you can follow this. You've got, again, in three-dimensional space. So here we are in three-dimensional space. We are going to pick a point in space, right? Any point we want. X naught, Y naught, Z naught. And we're going to create a vector that goes from the origin to there, right? That'll be R naught. So R naught is the vector X naught, Y naught, Z naught. So there was my point, right? I've got a vector going from here to here. Now, here's a second point on this line. Let me connect these together. Here's my first point. Got a vector going from there to there. Here's my second point, right? I now need the vector that goes from here to here, right? Right there. That's V. V will just be the we know how to get the vector from one point to the other, right? So from here to here, we create that vector, and that will be our V. We'll call that the vector ABC. Instead of AB, it's ABC, right? 3 components. And then it's the same generic formula. It's the same exact generic formula. It's R naught plus T times V. R naught plus T times the V, which now has 3 components. And then, don't you get 3 things over here instead of 2? So how many parametric equations do we have now?
3.
1, 2, we have 3 parametric equations, don't we? One for x, one for y, one for z. And we will have 3 equivalent expressions when we do the symmetric. Because for each of these you can solve for t, can't you? Solve for t here, solve for t here, solve for t here, and then set them equal to one another, and you will have 3 things set equal to each other. This is the symmetric equation for a line. I think we should do an example.
Yeah.
So there's a point, sorry, there are 2 points in 3-dimensional space, right? 2 points, there they are. First thing I'm going to do is I'm going to create a vector that goes from the origin to one of those points. And I'll stick with the first point I see there. This is going to be my R0. This is the vector 3, 6, negative 4. So again, I've got my line in 3-dimensional space. I've got 1 point. This is the 3, 6, negative 4. This is the 7, 14, negative 7. I've just created the vector that goes from the origin to here. Now I need the vector going from here to here. And that will be v. So v goes from here to here. That is the vector 4, 8, negative 3. Everyone got that? I'm going from here to here. So I take 7, take away 3, that's 4. 14, take away 6, that's 8. Negative 7, take away negative 4, same as adding 4, you get negative 3. That's my direction vector. Got it? So now r of t is equal to r0 plus t times v. And that is now, let's see, 3, 6, negative 4, that's my r0, plus t times the direction vector, which is 4, 8, negative 3, which can also be written as 3 plus 4t, 6 plus 8t, negative 4 minus 3t. So what I did there, all in kind of one step, is I distributed the t through to all 3 of those components, and then I added them together. Put it all together like that. That answers part A. Questions? Part B, find the parametric equations. Well, they're right here, aren't they? Those are your 3 parametric equations, x, y, and z. So I'm going to answer part B right here. For part B, this is the answer to part A. For part B, I'd write x equals 3 plus 4t, plus y equals 6 plus 8t, and then z equals negative 4 plus minus 3t. There we go. Those are your 3 parametric equations. Find the symmetric equation.